Excellent, very good. Well, thanks so much for having me here. And actually, I realize this is my fourth talk at Berkeley this year, but they've all been different. But I think Berkeley's definitely working me hard. Make sure I always have a new paper or an old paper. This is actually an older paper, and when I was trying to decide what to, well, older, but yet I'm still working on it. So this is the world of economics empirical work where we spend 4 years or 5 years writing a paper. When I was thinking about what to present today, I was looking at the schedule and sort of thinking about the broad range of things covered, and I felt like it would be good to give a paper that was really kind of in the heart and soul of the way that economists have been working with data in a way that's sort of a little bit different than what some of the other disciplines have been. And in particular, the way that we use, this work is going to use modeling assumptions more. So I actually wanted to start out by just taking a little bit of a cue from Duncan's title from yesterday. Sadly, I had to teach 3 hours yesterday, so I wasn't able to make it. But I saw he was talking about sort of problem-driven social science. And I really liked that title. I don't really know what he said, but I'm sure it was all good. Anyways, one of the things that groups that before I really had this passion for big data, I was helping organize the economics profession's field around market design. And one of the reasons that I was really drawn to that area is because it's really a multi-method approach. And so in economics, people are actually probably more than some other disciplines tend to be very narrow in the methods that they use. Not even just, when I was a junior faculty, I was told my empirical work wouldn't count for my tenure because I was a theorist. And even within empirical work, you're like religion A or B or C, but you don't often do all of them together. And I've always been more interested in using the best method for a problem. And so market design was one of those areas where we would have conferences that actually had theory and experiments and empirical work of all different stripes. And we didn't even really comment on it. And I think part of that was because we were all trying to solve a problem. And so I think that organizing around a problem just kind of breaks all of the barriers down. And that was certainly my experience working with Microsoft when, you're trying to build a product or make something work, you're going to try, you just want to make it work as well as possible. And people tend to lose their religion at least a little bit. So just a bunch of different large, important real-world markets that have been designed and analyzed in interdisciplinary collaborations, residency matching, school choice, and kidneys. These are all things that Al Roth and Parag Pathak and a bunch of other economists have worked on in very close collaboration with policymakers where they've really changed the market design. Spectrum auctions, and then more recently like ad auctions. An economist redesigned the Uber surge prices, and so these are cases where economists are working very closely either with the policymakers who sort of own the design or the engineers who build it. And so then in economics, bringing out this sort of methodological theme, let me talk about some of the different empirical methodologies that are used. And again, within economics, people have often very, very strong religions about what they do and how they do it. So, you can sort of start with sort of descriptive work, which is like facts and correlations. So, like Matt Jinskow has very nice work about empirical news browsing, and he shows, well, people who read extreme news also read news from the other side of the political spectrum. So those are kind of facts that might be important for then driving further work. That is a minority. You typically don't get published in the top economics journals for descriptive work, but occasionally if it's an important set of facts, you will. The next set of things is like theory testing. So like in some of my work, I've tested whether, first price auctions or ascending auctions raise more revenue, which ones attract more small bidders. Now, to make those kinds of test those kinds of predictions of theory, you do need to assume all else equal. So in my setting, there was actually random assignment of the auction mechanism. They like drew balls out of urns to figure out what kind of auction to run. That's relatively rare, and in that style of work, sometimes people aren't quite as careful about their statistical assumptions. Then like a very large literature, and this has sort of a stronger religion around it, is sort of causal estimation of policy. So this tends to be like what happened when we changed the minimum wage. That's a huge one just by itself, huge literature. What's the effect of a labor training program? And it's generally what's kind of distinguishes this is that it is a policy. You're estimating effect of an actual policy, like giving mosquito nets to people in Africa, changing class size in Africa, giving food at school. And you're estimating the effect of the actual policy. And so generally some people got the policy and some people don't. If you're lucky, you do randomized experiments, and then even within this literature, there's a little bit of a war between people who think they should only do experiments and people who think that we might be able to use observational data to answer those questions. You always need some assumptions because of Holland's fundamental problem of causal inference, that is, if you don't observe the same unit with and without the treatment, I can't know what would have happened to you if you had not had a bed net because you had a bed net. And so you must have an assumption. At a fundamental level, there's a missing data problem. I don't see you in both states of the world, so there's always assumptions. They're not very strong if you ran a randomized experiment. If you didn't, things like unconfoundedness, that is, you observe all of the confounders, that might be high dimensional. And instrumental variables is also a super popular technique in economics, where you have something like the draft lottery number that makes you more likely to enter the military. It doesn't directly determine whether you go in the military, but it changes your probability. And so the frontier right now in econometrics in this thing is trying to bring this into high dimensions. That's my most active area of research right now. I just posted a paper on Archives yesterday about high dimensional and confoundedness. I've also been working on heterogeneous treatment effects and so on, combining machine learning and econometrics. Then the last area, which I think is less well known across the interdisciplinary audiences, and that's what I'm going to do today, is structural modeling. And in structural modeling, you're actually going to make a few more assumptions beyond the statistical assumptions. You're typically going to make assumptions about people's behavior. And from their behavior, you're going to infer something about their preferences. And so why would you do that? Well, what if I want to make a prediction about what happens if I change my auction format? What if I want to make a prediction about some policy that's never been implemented at all? What if I want to look at the welfare effects of Target and Walmart merging, Staples and Office Depot? Those types of questions economists are asked to answer, and in fact they get paid a lot of money to answer those in court cases. A big business is like helping the DOJ or the FTC decide whether to allow mergers, and those are worlds where you cannot validate the thing because it hasn't happened yet, and you want to figure out welfare. That is, I want to know firm profits. I want to know people's consumer utility, and how could I possibly know how you feel? Right? I mean, that's what I'm measuring. I'm measuring how you feel. Well, the only way I can possibly do that is I need to assume that your choices reveal something about how you feel. So that's a behavioral assumption, that your choices were optimal. If I don't make any assumptions, I obviously can't measure how much worse off you are, nor can, if I don't make any assumptions about the firms, I obviously can't predict how much they're going to raise their prices. So we're kind of put into this bucket not because we love making assumptions, but because we are asked these questions and they're going to answer it. I was asked at Microsoft, what would happen if we got Yahoo's search business? How many advertisers will we get? How much will revenue go up? They're going to make a $30 billion decision based on that number. And you got to come up with something. So we do it because we have to, and there's been a lot of work to try to relax assumptions, test assumptions, and everything else. This could be a Bayesian or frequentist model. My model today is going to be Bayesian. Okay. So now let me dive into the problem at hand. I'm going to talk about advertisers on Bing. And so in terms of these structural models, where this paper is new from an economics literature perspective, is that typically one reason that some religions didn't like each other in economics is that people didn't like the idea of making all these behavioral assumptions. So my first take at kind of advertising auctions would say, well, as a structural economist, what would I do? I'm going to assume the firms are profit maximizing, and I'm going to figure out if their bids were optimal, I can figure out what their values would have been, and I can predict what would happen if I make a change. And that was the question I was asked, so I needed to do that. But those models didn't do very well predicting. They just kind of ran into some real bad empirical facts. Half the advertisers didn't change their bids at all over a 2-month period, and that obviously any rational model, their world was changing, they weren't changing. I was failing miserably on half the advertisers because I was predicting that they would change, so I was just making really bad assumptions. And furthermore, if you kind of talk to the advertisers, which I also was kind of part of the work I was doing at Microsoft, you saw that they were using these tools and they were putting in all sorts of other objectives into their bidding strategies. Computers were bidding on their behalf and not the way that I was putting them in the model. So that both made the model predict badly, and it also made the engineers not so convinced by my model. And because I was an economist, the fact that this is what people always did carried zero weight at all. So I needed to make my model better. And so that's kind of what we set out to do. So generally, though, I mean, part of the reason we needed this, why were they asking me to do it? Well, the markets are actively designed. Reserve prices, matching algorithms, scoring algorithms, all are things that are getting changed all the time. And all of these change advertiser behavior. So if I do better click prediction, that means that I'm going to accurately predict that people aren't going to predict on some ads. That's actually going to thin out my auction, and that has an effect that the bidders should reduce their bids, for example. So if I don't predict that, my short-term A/B tests give me garbage. And like in a lot of cases, the short-term A/B tests that don't account for these long-term responses go in exactly the opposite direction of what should happen. And it actually, I have a whole huge talks that I give about this because this is a huge passion of mine, that all these large tech firms are sort of innovating in the wrong direction sort of systematically because they only measure short-term effects. And it's bad generally. You can think of all the mistakes you make on the user side from doing that, but it's just horrible on the advertiser seller side. Okay. So then because of this, but you can't, and I have other research on trying to fix these problems with better short-term measures, surrogates, advertiser level experimentation. That's noisy, the power is terrible, it's expensive, it's disruptive, it's slow, the advertisers don't like it. So the structural models can be another tool in the toolkit. So how does this work in advertising? Well, so what happens, the user enters the query, the deliver engine is going to query the database to get the applicable bids. There's going to be a scoring algorithm to produce the scores. The ads are selected, ranked, and scored, and then the user clicks on the ads. And then the process will repeat for a new user. So you can think about from the advertiser perspective, they're going to place a bid, and then this process is going to happen over and over again. And one of the key features of this is that the environment's actually very stochastic from the perspective of the advertiser, because new scores are drawn every single time a query comes along. Other people are running out of budgets. There's all sorts of randomness in the system, so they actually face a smooth problem. The early kind of game theory literature on this did not account for the smoothness, and it actually made the problem much harder. And people got kind of completely off on an irrelevant tangent about multiplicity of equilibrium and all other stuff that had nothing to do with the real world problem. So just to kind of see, it's a generalized second price auction. They place a per click bid. There's an estimated revenue bid, which is the quality score times the bid. The price per click is the minimum price they could have bid and still maintained their position. So if you think about tying their estimated revenue bids, you get to the price per click. And then this is how much revenue you get from each position. And one of the sources of randomness is just to show these quality scores are random from the perspective of the bidder, which is what makes the problem smooth. So previous work, as I mentioned, kind of got hung up on the discreteness. In an earlier paper, we developed the theory of the continuous bidding strategies, developed the equilibrium, showed existence and uniqueness. And we estimated this model under the assumption that everybody was maximizing profit per click, which is from clicks, which is kind of the standard place to start. As I said, we didn't do a good job fitting the data out of sample for the reasons I mentioned. But just to show you how our new model is going to incorporate that model as one component, so let me sort of show you how it works and give you a sense of how you use behavioral assumptions to infer valuations. So here on the x-axis is the expected quantity of clicks. What you can read directly off of the data is the average cost per click as a function of how many clicks you want to get. Well, you don't directly read that off the data. What happens is if I take all the auction data, I can rerun all the auctions using the auction logic, because I understand the logic, at different levels of bids. And as the bidder increases their bid, they're going to be in a higher position more often. They're going to get a higher fraction of the available clicks. But they're also going to pay a higher price as they move up the auction. So each time they raise their bid, they're going to be more likely to be in, say, this position rather than this position and paying a higher price, but they're going to be averaging that out. And so if I can basically do this, this is not really it's not statistical estimation. It's kind of numerical approximation from what I see in the data. I can then numerically differentiate it and get the marginal cost curve. So in our first paper, we actually did this all non-parametrically and did the numerical differentiation. In the second paper, we actually used a log normal functional form because that made our results much more stable and it fit the data reasonably well so that we didn't end up with irregularities in this numerical derivative. Once I have the numerical derivative, this is the marginal cost curve. Okay, then I have something that looks like we teach in Econ 101, except for you're buying instead of selling. And so in particular, the optimal solution from an profit maximizing advertiser's perspective is that the value per click should be equal to the marginal cost per click. That's the first order condition for optimization. So if I saw this advertiser buying half of the available clicks, and I have estimated this marginal cost curve, then I can say, all right, what value would, at this observed quantity, would set the value equal to marginal cost? And that's the green line. That's what I'm inferring. And so that's like about 0.78. So I'm inferring that in order for the bid that they chose, and therefore the quantity that they chose to have been optimal, they must have had this value. And this is the profit they get, the value per click minus the average cost per click. This is the rectangle they're trying to optimize. And to maximize, they want to make that rectangle big. And value equal marginal cost is what does that. So this is what we did in our first paper. And we figured out these values. Let me just skip over that. So let me show you the data that we have now. And we're going to build a richer model. So we've got 9 months of data in our sample. And we have roughly about 80,000 accounts on average in each month. Then each account has lots of listings. So we have somewhere between like 1.5 million and 3 million listings in our data set in every month. And a listing is like a keyword bid. So it's like auto insurance, exact match, and then a bid associated with it. That's the level at which we have the bids. They're active on average. The listings kind of come and go, so they're not all there for the entire time. So it's not a completely balanced panel. And then this is the average number of queries per listing. So each listing on average is showing up not very often, but that's a very skewed distribution. There's a lot of very big ones, and then a few ones that don't get a lot of action, and then a bunch that don't get a lot of action at all. All right, so the empirical facts. So there's a lot of heterogeneity in participation. There's also a lot of infrequent bid changers. There's also listings created for very different purposes. Like some of them, they'll be actively managing, and some they won't. Some of them are on like eBay bidding on eBay, and then they're going to set a very high bid and just leave it alone. Other ones are going to be like broad match, where they don't really know where they're getting matched, and they tend to optimize those indifferently. So today I'm going to show you what we do for frequent bid changers, and because that's the easiest one to explain. So what do the advertisers know? Well, first of all, they can see their average clicks, average CTR, average CPC, and so on through the online tool. But in addition, there are tools that allow them to basically do counterfactual. So the tool will actually let them see what would happen at different bids. They're noisy, but they'll give you some idea. And the advertisers can also experiment. They use a bunch of tools that help them optimize. I love some of these things. They do like, a self-learning algorithm with flexible configuration and so on. And like, optimization is like part of it, which is very funny to an economist because like, what is this tool for? It should just be optimizing. Like that shouldn't be a feature. That should be the point. But anyways, so one of the very interesting things is like when you use these tools, they actually give you lots of goals. So like one goal could be to like maximize profits from actions. Another one could be to get the right position. Another one is to try to spend a budget efficiently. So you can actually tell these tools to do a lot of different things, and so that's something that we're going to want to account for. Some of the funny things are that some of these goals are actually like just don't make sense under any circumstances, but they are offered anyways, which is kind of funny. But so anyway, so let me talk about the ones we're going to look at today. I'm just going to show you 3 different objective functions. One is that they maximize profits from clicks. One is that they want to get impressions, which is often what they say they want to do with their brand keywords. And also I'm going to let them have an incremental value from being at the top of the page, which is, again, another thing that they often try to do. And their action space is a space of bids. So for each bidder, I can write down their total expenditure, the click probability, the probability of appearing, that's an impression, and also the probability of appearing at the top. And so I can write down the profits from these different objectives. I mean, the notation isn't too important. It's just to say that for each of the objectives, profit from clicks, from impressions, and from appearing in the top position, they're all functions of bids. They're all smooth functions of bids because of the uncertainty. So I can differentiate all these objectives, and for each of them, I can invert them to figure out for each bid what values would have made those optimal. So the model is basically that the bidders, there's going to be latent variables. It's going to be a Bayesian model. So I can think of the bidder as having a latent type, but I just don't know which one they are. And then there's going to be parameters for those objectives. The distribution of the environment changes over time, but the bidders are learning that and figuring it out. And so what I'm going to assume is that whenever they change their bid is optimal. Okay? And so the way that I'm going to infer which type of objective they are is I'm going to say, suppose I see them over 9 months, they keep, they make, the world changes frequently, and I can observe that happening. I see them responding to those changes in the world. I can see, suppose one of the objectives, if I assume they were trying to get in the top position, their behavior doesn't make any sense at all. Like, I would have to have their values varying wildly in order to make that objective make sense. But then, on the other hand, maximizing profit from clicks, I might have their value for click being relatively stable over time to be able to explain their behavior from a value per click model. So I'm going to use stability of the preference parameters as my metric for saying which objective makes the most sense. I'm going to say the objective doesn't make sense if you would need wildly varying preference parameters to explain the data. Now, this is obviously like a strong assumption. We can project, we haven't actually done this in the estimation I'm going to show you, but we can actually build an underlying stochastic process to allow those costs to vary by time, by day of week. And I have all the data about what the other bidders are doing. So I can build an underlying stochastic process into that estimation because that assumption that they're just constant over a 9-month period is obviously not reasonable. Okay, so the idea of identification is basically that at the instant of the bid change, the bid is optimal. I'm going to recover the parameters for each possible objective function. I'm going to use the stability criterion to choose the objective function. And then again, as I mentioned, I can allow those preferences to vary over time. I said all that. And so, to a little more specifically, the way I'm going to do this from a computational perspective is there's all these components of the objective function, and I'm going to estimate all the derivatives of all of those components. And actually, to do this, I'm going to go query by query. Since I'm modeling the uncertainty for each query, I can take the derivative of all of the different components. And I can do that in a parallelized way. So I've got, whatever these like 300 million things, and I can parameters, but I'm going to be able to figure them out because for each individual user query, I'm going to calculate a derivative, and I can just take all these derivatives and then aggregate them back up again. And so basically we do this huge thing on the clusters, but then we can pull it off and on a server do my Bayesian estimation once I have all the derivatives. So the Bayesian estimator, I'm going to have a prior over the types. The likelihood is defined for the process of the transition of preferences over time, and the overall likelihood is a mixture of the likelihood of the different objective functions. What I'm going to output is the posterior over both the parameters of the objective functions and the type of the bidder. And this is nice relative to, say, frequentist approaches, because I'm going to really understand some bidders well, and other bidders I'm not going to really have a lot of data about them, and so I'm not really going to know much about them. In what I'm showing today, I'm only going to use bidders who change frequently and who don't do it like every Monday, so that I can sort of say that it looks like they're actually being optimal about what they're doing. And I'm going to assume that they look at the most recent data when they change their bid. So the idea is like they're monitoring, and then, oops, it looked like the world changed. I'm going to log in and change my bid. So the Bayesian model is going to basically be a classifier over the objective functions. And so luckily, this is a very sharp classifier. So I'm basically, for almost everybody, I'm getting that either they have an objective function or they don't have an objective function. Now, this is a little bit, it maybe looks a little better than it is because, I mean, these models make very different predictions. So it's sort of unlikely that they're both all going to give the same kind of goodness of fit. So it's, but nonetheless, it's good. There's a little bit of math here in the middle. Okay, so then what are some of the main results? So one of the things, this is really the chart that actually got us the most excited or made us feel like, okay, we had a model that really worked. We looked at the different match types of the bids. So exact match is eBay bidding on eBay and only on eBay, or like bidding exactly on auto insurance. Phrase is that the search term had to have that same phrase. And broad, like basically like you could be on anything. It's just something that the search engine thinks is sort of like your query. And so usually for broad match, you're not thinking about being in the top position. You don't even really know where you're being shown, or you don't really understand it very well. So you tend to do that as like more like just generic direct response, where you're just looking at the data and optimizing, while the bidders are caring a lot about how they appear on exact match listings, because a lot of that is brand. And so what we see is that most of the exact match, or like about half, we're classifying them as valuing being in the top position, while for broad match, we're seeing more than half looking like they're valuing clicks. And so that's roughly sort of what we would expect. It's what the advertisers tell us. And so, you know, we found that really reassuring. Then we could break out our results by industry. And we found that like autos, financial services, and travel and transportation looked like they were really optimizing for clicks. And again, these are industries that are pretty sophisticated, that are generally big, high value, have big automated in-house. Like I'm on the board of Expedia. They have this huge in-house thing where they're optimizing their search spend in a very scientific way. While over here, like entertainment and investments are high on the impressions, and you can think of that as maybe being, again, a little bit more brandish advertising. We find that a lot of heterogeneity within accounts. So we find that this is the fraction of the listings within the account, that the empirical probability for all listings within the account being the same as each other, and roughly like a little more than half of the accounts are like all the listings look like the same type. But there's actually a lot of heterogeneity within accounts, and that's, again, consistent with what we expect. And there's actually not a lot where everybody in the account is just trying to be in the top position, which, again, is sort of what we expect. Let me just say a few more words now. Actually, I don't really know when I'm stopping because we started late, but something like that. Okay. So then the final thing and this is one of the reasons we're still working on this, because we've been trying to incorporate a lot of extensions to make the model more and more realistic. One of the really important things, but that actually required a fair bit of change in our terms of our computation, is dealing with budget constraints. So in practice, many advertisers have budget constraints. And so I said before, like everything was all separable. Like I could go out and calculate all these derivatives, you know, kind of user query by user query, and then aggregate everything up. And I say, oh, I've got, millions and millions of listings, but each of those was done completely independently. So I could have written this paper with 200 listings or 3 million, but I didn't do anything differently. It just sounds really cool that I'm estimating 50 million parameters, but it's actually like not any different than doing, a couple thousand in terms of, except just I need more computers. But one thing that makes things non-separable is budget constraints, and because that then links the different listings in the account through a Lagrange multiplier. So what happens on one listing would make you want to bid less on another listing. And so if you just have one listing, you can't actually distinguish that Lagrange multiplier, which is going to make you want to sort of bid less aggressively, from just having a lower value per click. So I need a more complicated estimation scheme for that. And then I also have to worry about the budget constraints changing over time. So what we basically do here is we use a Bayes empirical likelihood approach, where we have these moment conditions. And one of the moment conditions is the covariance between the bid change for the listing and the spending on other listings in the same account. So if they didn't have a budget constraint, the spending on other listings on the same account shouldn't be correlated with the spending on this listing. They should be the bid on this listing. They should be independent. But if they do have a budget constraint, that would create the link. And so it's that link that's going to allow us to back out how much this budget constraint is binding. This is a trickier thing to do for a whole bunch of reasons. And you also have to start worrying more about, well, gosh, like maybe there's something else that's happening at the account level. So we tried to bring in a lot more control variables for things that are happening on these keywords. So we want to essentially find something that looks a little bit more like an instrument. So we don't want to say, oh gosh, this advertiser is spending more on red roses, so that means that and that affected what they did on pink roses, therefore they're budget constrained because maybe there's something going on that's making them bid differently for red roses and pink roses. But if users were searching more for one of those queries, or if something was happening outside of their control on one of those other queries, then that would give me like cleaner, better variation to identify the budget constraints. So we've been trying a bunch of different methods to get sort of the cleanest possible variation for identifying the budget constraints. And then the base posterior is this mixture of empirical likelihoods. So what do you do with all of this? Well, then you can deliver on the promises I made at the beginning. For example, I can predict what will happen if, say, I make my click prediction better, or I make better matching algorithms for ads and I thin out the auctions. I could accurately predict that the bidders will, once they realize there's not as much competition, will further reduce their prices. Another thing specific to this model is that, gosh, like I found the whole auction is designed for advertisers who care about clicks. We don't allow them to express a value for impression. We don't have a product that says automatically bid on your behalf to stay in the top position. So Bing or Google could offer that kind of product, and that would improve efficiency for the advertisers. And so there's various market design implications once you understand how much of the market just wants to be in the top position. And generally, you want to weigh welfare for advertisers with high costs of optimization. The fact that we see advertisers not making changes even though we think they should, we should realize that we're inflicting costs on them when we change the system too much and make the system too variable. Okay, so just conclusions. There's lots and lots of heterogeneity in this e-commerce application. And I think you would see the same for sellers on eBay or advertisers on Facebook, marketplace sellers on Amazon, highly heterogeneous actors. But modeling them is super important in a world where it's really hard to do A/B testing. So this set of techniques can classify the advertisers, get parameters of their objective, and really help guide your thinking about how to design the marketplace better. But I have to say, like out of everything I ever did in tech firms, like this kind of had the least buy-in because people don't understand all these assumptions. They understand an A/B test, even if the A/B test is like patently, blatantly, obviously wrong and like idiotically wrong. People are happier with that A/B test. The A/B test is essentially holding the advertiser behavior fixed. So you got to ask yourself, would I rather make an assumption out of this model where I made a lot of bad assumptions, but I'm assuming the advertisers are doing something, or would I rather use data that did not allow the advertisers to respond at all and actually just assume the advertisers never respond to anything? Well, it seems pretty clear to me that this is sort of better, but it's just not. I've had some people in industry get excited about it and buy into it for periods of time, but I think it's just very hard. I think it's partly because it just doesn't really fit into the classic supervised machine learning kind of paradigm of having a test set and sort of seeing how it all works out. So that's my caveat at the end of this. I love the research has been really fun for me to do, but it hasn't been as impactful as some other things I've done. So thanks.